Well, let's get started. So thanks everyone for coming to the first live stream that we've done. This is my first time doing this, so it's going to be a little casual. And what we're going to do today is go through a Jupyter Notebook, a tutorial on using inverse kinematics on stretch. It's I mean, before we get into that, just on the call here, we've got so myself, I'm Benit Shah. I'm a software engineer at Hello Robot. I've been here for about 2 years. My moderator is Chintan. He's been here about a year. And we've got students from Georgia Tech and CMU. I'll start with sharing my screen. What we're going to do is go through the tutorial for about 20 minutes. I'll just talk through some of the initial theory and in practice how you can do that. And then actually we'll just, for 25 minutes, program a demo using that code live. I don't know how that'll go, but I'm excited to try it. It's going to be using that IK code that we created in the tutorial to try to get something on this whiteboard. And then I guess I'll start with announcements. So this is the first workshop that we've done like this. We're hoping to do more. Most likely the next workshop will be related to reaching to a Aruka marker. So typically when you want to do autonomy, a really nice way to make it a little more determined and easier is to add an Aruka marker tag. It's like a sticker onto whatever object you want to grasp or whatever environment you want to manipulate in. And so a common thing there is like, can the robot just go to it and reach for it or grab around it? And that's going to be a series of workshops that we do in the upcoming weeks. We'll have announcements for that on the forum here, just like this post right here. It'll be in the announced category. So be sure to keep an eye out for that. And then the other announcement is we have a event that we're going to be at Hello Robot. We actually have a booth at HREF. It's this conference in Boston at the Robotics Summit. I'm not sure if any of you guys are planning to make it over there, but feel free to come by and say hi at the booth. One of our engineers will be there. So without further ado, let me go ahead and get this tutorial started. So this is what a Jupyter Notebook looks like running on my machine. And what I've actually set up here is my computer, the one I'm sharing this video feed from, is SSH'd into the robot. And so I can actually run all of these robot API type calls directly from this notebook here without having to be on the robot with the HDMI cord or tethered in any way. There's a little bit of instruction here on like how you set that up. In particular, this is the trick right here. But in general, this tutorial, it's not too, it's made for like a beginner level, so it should be pretty easy to follow. So going through the first few steps, what we're importing in this is the library that's going to kind of do all the magic here for us, is IKPy. It's the inverse kinematics Python library that's going to do all the IK solving for us. In the next cell here, I've imported stretch body. I've created a Python instance of the robot class. So this is how you do that. You say R or robot or whatever your variable name is equal to an instance of stretchbody.robot.robot. You can call startup in order to connect to all the USB buses on the robot. And then over here, I'm just fresh booting up this robot, so it's not calibrated yet, which is why it just went through a homing procedure. And that's what you see here. Okay, so a little bit of what is inverse kinematics. I've said it a few times now. So with this, what we're trying to do is talk about a common problem in robotics of getting from a robot and trying to get it to hold its gripper or some part of its robot parts at a certain place. And that's very vague, so I'll try to build up to that. So one way that people have characterized robots and this is really popular, is as a chain of links connected to each other by joints. And that kind of comes from, like you can think of like a human as its arm is very similar, right? You've got links for your torso, your upper arm, your forearm, your hand, and you've got joints in between each of those links. You've got your shoulder, elbow, wrist, and altogether we are able to perform the computation in our head needed to reach to a certain position and grab things out of 3D space, right? And so that's the high level goal, is to do something similar with the robot. On Stretch, this image shows all of the links and yep.
I'm sorry to interrupt. Could you zoom in a bit to improve the visibility?
Oh yeah, for sure.
Yeah.
This image is kind of difficult to read on purpose, so don't worry too much if you can't read it. Actually, we're going to generate this image again live based on the robot that I have behind me in a few seconds, so it'll be in more detail then. But what I really want to show is kind of this part off to the left here. On Stretch, what are the main links or what are the joints to be aware of? So this is the base link. It moves around the world, and actually that's for mobile manipulators, you'd hope that the base link can move around the world. But with like fixed off arms or like industrial arms, typically the base link is fixed and you don't actually see it moving. You have a joint for the lift. This is the joint that can go up about 1.1 meters. You have 4 joints for the arm. This is telescoping and it allows the arm to expand out to about 0.5 meter. You've got, with the dexterous version of the robot, which is a specific gripper for the robot, you've got 3 joints here. This is pitch, roll, and yaw. And then with the standard gripper, there's just yaw. And then at the end, you've got a gripper. So the gripper is a compliant gripper. It has a grasp, a link there. It's called the link grasp center. That's right in between the fingers, and it's pointed out directly out from where the fingers are oriented. It's a very useful link to plan for, because what you can do is you can ask some planner to get that link grasp center onto whatever object you want with the gripper's fingers totally open, and then you can just command the gripper to close, and now suddenly you have your grasp for whatever object you want. This is that chain that I'm talking about, right? So how do we go from base link all the way down to link grasp center here? And there's a fair amount of stuff in this chain. In this chain right here, actually, on Stretch, there's also a head here, and that's not what we're planning for, so it's not labeled here, but it can take you all the way down to the camera link. And you could imagine using this exact same algorithm to try to solve for, I want the camera to look at a particular thing. How can I use this chain to get it to look at that thing? So the robot is a chain composed of links and joints. That's great. A few other things that we need to know. So robots, when we talk about their joints, when we talk about them being in a certain position, we're talking about basically like the lift maybe being in its range from 0 to 1.1 meters. It's maybe halfway there, so it's like 0.55 meters. And maybe all the other links or joints are at their 0 value. Those are called configurations. So these are robot configurations that the robot can take. Typically called like the configuration space is the total space of possible configurations for the robot. And that's in parallel to the task space, right? So if you think about the configuration space, it's maybe prismatic joints, prismatic meaning sliding, right, like on Stretch, or revolute joints, meaning rotational joints, versus task space, which is I have an object that is oriented with 3 rotational angles and with 3 positional X, Y, and Z positions in 3D space, right? So 2 different spaces here, and the fundamental problem between forward kinematics and inverse kinematics is going back and forth between these 2 spaces. So with forward kinematics, you want to go from, hey, I've given you the robot's lift is at 0.55 meters, the arm is at 0.3 meters, the rest of the joints are at X, Y, and Z. Tell me where that link grasp center is in the task space. For inverse kinematics, we're trying to do it the opposite way. We want to go from, I have a desired position for the link grasp center in the task space. Take me back to the configuration space. What are the joint values that I need to achieve that? This right here, I'm not going to highlight too much on the math. I mean, end of the day, we're actually going to let the library handle a lot of this, but I do want to give you a sense for how this works, right? So when you talk about configuration space, you typically call it Q. It's just a common denotation for it. And it's in a space called r raised to the number of joints that you've got. And then when you talk about the task space, you say you've got some X, and it's in a space that composes the task space. And for most 3D worlds, that's SE3. So SE3, Special Euclidean Group 3, is a term from Lie algebra. It can get a little complicated, but I'm not going to give a primer on Lie algebra here, and we're just going to breeze past the math a little bit. If you can imagine that you've got some tasks and you've got some configuration, then f is your function that takes you forward, right, from the joint space configuration into some task. And inverse kinematics is the inverse of f, where you've got some task, you give it to that inverse function, and it gives you q. So one thing is, actually for like simple robots, you totally can solve this analytically, right? For kinematics, for like a triple R arm, that's a very common theoretical arm to talk about, where you've got 3 joints and they all rotate. You can absolutely talk about that in a system of equations that you can represent in a matrix, and you can solve for it the inverse analytically just by going for the arctans and the arccosines and all that. We're not going to do that. We're actually going to solve it iteratively. One, because it would be very difficult to do the inverse here analytically. And 2, because we often have multiple joint configurations that would succeed in getting you to a certain goal pose. And so when you do this analytically, you have to account for either there being no solution or multiple solutions, whereas the iterative approach, it'll converge on one based on the starting configuration we give the solver. The approach that is used inside of IKPy, and it's actually very popularly used when solving for IK iteratively, is called the pseudo-inverse Jacobian method. And we'll get into that now. So in order to explain this, I kind of wanted to take a simplified version of Stretch. So this is Stretch in a top-down 2D world, taking a bird's eye view at the robot. You've got still the differential drive base, differential drive meaning 2 motors side by side in the mobile base. You've got no vertical arm because, we're top down, but you do have the telescoping arm. And so this blue bit, where it is on the red, that red line is telling you how telescoped far in that arm is. And then the blue is the yaw gripper, so that rotates around, and the goal pose is given here in yellow. So for this simplified version of Stretch, the configuration is given by these variables, x, y, and heading for the mobile base, S1, which is how far extended you are along that telescoping arm, and theta 1, which is the orientation of that the wrist yaw joint. So this is actually really easy to write a system of equations for. I want to get the end effector x and the end effector y and the end effector heading. I take in these variables, the configuration variables, and then forward kinematics is given the x of the base, I need to also solve for the x component from that arm, and also the x component from the yaw joint, right? All that sum together gives me x. Same thing for y. And then heading is just going to be heading of the base plus heading of the yaw joint. This is where you take the system of equations and we take partials of it, right? So when you've got a system of equations and you take partials with respect to each of those configuration joints, what you're creating is called a Jacobian. So a Jacobian, it's used pretty commonly in robotics. You've probably heard of it before. It's usually pretty difficult to do it by hand, but nowadays we've got like symbolic computation libraries. I use something called SymPy here. It's a very popular library. But what you're aiming for is J, your Jacobian, times the partial or the derivative of the joint vector is going to give you x dot, the change in the task space, right? And so already you can kind of see now, if you can get J, how you can start solving iteratively. If I know some iterative change in Q, I can find some iterative change in X, right? So ptosis in the SymPy gave out this matrix right here. And then we've got x dot equals J times Q dot. That's not really what we want though, because what we want is Q dot, right? We want to know what is the change in configuration in order to get to the desired X position. So what we do is we take the pseudo inverse. Often this matrix doesn't have an inverse it can be solved for because it's singular in some way. So what you can do is you can take the pseudo inverse, and actually using SymPy again, if there is an inverse, it'll give you just the true inverse. But this is really nice. So now I can say, hey, given some change in X, what is the change in Q, right? And that's the J raised, this is how you denote the inverse or pseudo inverse. You had a plus sign there. So this works. You can actually see, I wrote in another notebook, this is visualization of the iterative solve, basically over and over giving that delta in X and changing the goalpost 3 times. And then this diff drive and arm toy robot being able to actually solve and get the end of that blue joint there attached to the land on the goalpost. Usually you wouldn't want to visualize it this low, right? You'd want to just solve for the end goal and execute it. But this is also kind of where a few other things about the toy example fall apart. One, there's no offsets at all. Every single joint starts exactly where the previous joint ended. That's not true in Stretch. Things take up real space in the real world, so you have to have offsets. So this is where it's nice to bring in an actual library that handles all that. So what I'm going to be talking about here is a paradigm for doing inverse kinematics on Stretch. The idea is we actually don't want to use inverse kinematics to do complex things like obstacle avoidance and path planning, because frankly, inverse kinematics, you'd have to continue adding constraints for every single object in the environment, and it's probably not going to be able to solve, and it gets kind of frustrating. Instead, you want to use something like RRT or potential fields, or just libraries like MoveIt or FunMap in order to actually get the robot in the general vicinity of the manipulation space. That's the step 1 here. Another option there for planners is the nav stack. Then you can use something like aligning. So this is something that we have in FunMap. You can align Stretch with the surface where you're going to manipulate. And then you can treat mobile base as a prismatic joint. So suddenly the mobile base is locked. It can only go forwards and backwards. And this becomes your x-axis. So if your mobile base is the x-axis like this, and your lift is your z-axis up and down, and your arm, which is orthogonal to both of those, becomes your y-axis in and out, you've got a Cartesian manipulator, something that can get to a point in x, y, and z space, right? And this is where we can introduce that IK method. So that's actually what we'll do in this tutorial. And, yeah, so let's go ahead and talk about how we do that. So in the world of robotics, a common way to represent robot chains is through URDFs. URDFs are a description format. They're XML code, or not code even, they're just XML. In Stretch's URDF, we have it in a few different places. Basically, we've got it in the ROS workspace that's on your robot, also in the ROS2 workspace on your robot, and also in the Stretch user directory, which is a directory in your home folder, and it has, all of these have the calibrated version of the robot. Calibrated meaning that the robot has realistic offsets between its joints, because it's actually looked at itself using those Aruka markers on the robot and seeing that what is the actual joint visually and optimized to get it really, really nice. A few, I think, notes here. So your URDF might not match the gripper you have on the robot. It's a manual step. You have to recompile the URDF when you physically take the gripper off and attach a new one. So if you bought a dexterous later and you attached it, make sure that you visualize your URDF and that it's the correct one. The two most common ones are the standard gripper and the dexterous. And then even more recently than that, in the dexterous version of the URDF, the link grasp center link was missing until February. So you definitely need to recompile your URDF if you want to follow this tutorial and you haven't compiled since February. Cool. So here, I think let's actually start running some code. So some imports, and then this is very similar to that diagram from above. This is that tree, that chain of the entire robot. And this is for a Stretch 2 that I have behind me with just the standard gripper here. It's got a lot of links. So I'm gonna make this an SVG because it's a little easier to kind of scroll through it. But it all starts with the base link, and it branches off in quite a few ways. You can see here it branches off towards the camera chain. But the one that we care about, we're going to follow the chain all the way down to the gripper to the link grasp center, right? So this chain kind of, going back to the bigger view, it kind of goes from here to there. We don't need the rest of it. We're going to get rid of it. And what we don't have in this chain is a prismatic joint for the mobile base, a translating joint. So we're going to add that in. And this right here, you can also look at the end-of-arm.name from that robot variable to actually tell what end effector stretch body thinks that you have. So stretch body thinks that I have the stretch gripper, which is true. I think another thing here, by the way, is there's a really nice way to visualize these URDFs as opposed to here where I have it as a graph in RViz, which is a visualization tool from ROS. This is the command you'd use on your robot, and you'd pop up a window like this where you could actually see everything visually, and you could actually mess with it in real time. Definitely check that out to get a better sense of what it looks like in 3D. But like I said, we're actually going to make some modifications. So the original URDF has 42 links and 41 joints. This cell right here removes all of the links that we don't care about. So now we've got 11 links and 10 joints. And this cell right here adds in a virtual joint for the base, which is that prismatic joint for the base. So this now makes it 12 links, 11 joints. And you can totally imagine if you don't want the base to move in any of this IK solving, just don't add this cell in, right? So I'm going to save that new URDF. This URDF got saved to temp IK tutorial stretch.urdf. And we're going to go ahead and import that back in and visualize it as a tree again. So now it looks like a single chain, starts at the base link, has a base translation joint, then the mast, then the lift, then the arm links and the joints, then the wrist yaw, then the gripper, and then the grasp center, and then it ends at link grasp center. One thing that I kind of breezed over here was all of this is done using a library called URDF Pi. That's manipulation for URDFs. But once you have a URDF saved like this, you could also just commit it somewhere and then use it continually. You don't need to continue to modify this manipulation URDF. So now for the first time, we're going to actually import IKPy, and we're going to create a chain. So that's going to be these two cells right here. And when you print out just chain, what you get is a bunch of links, kind of misnamed, actually really joints. So they're joint-based translation, mast, lift, all the arm links and joints, and then yaw and gripper and grasp center. And then this you can actually print out to get an overview, right? So once again, every single one of those joints with their type, so prismatic if they're sliding, their bounds, their range, right? Their offsets, these are those offsets I was talking about, the realistic offsets. And so you get that for every single one of the joints here. Okay, so one thing that we need to be able to do is read the current joint configuration of the robot. This is, where is the robot actually standing? So we're going to be using stretch body. We're going to be taking in a variable called the name of the tool. This is because if you've got the dexterist, you've got two extra joints to query. And the way this method works is it will return basically a array of each one of those joints. So let's just go ahead and run it. So hopefully you can see on the video the robot just stowed. That's because I called robot.stow, and then I called get current configuration, which gave me that array. So for my robot, let's see, so first guy is 0, second guy is the configuration of the base. The base has not moved, so that's going to be 0. This is then 0. This is lift, so that's 0.23 meters, so 23 centimeters. And actually that's correct. When the robot is in its stow position, the arm is about 23 centimeters high within its range. Then we've got another 0 here, and then we've got each of the arm links, 4 of them, because there's 4 links in the telescoping arm. Each of those are pretty much 0, e to the negative 7. And then we've got the yaw joint, which is at basically 4. That's 3.4 radians. The yaw joint, when it's pointed out, that's 0. And when it's looking back in the way it is right now, that's at 3.4 radians. Why do we have all these extra zeros here? Those map to these extra joints here that are fixed. Every single fixed joint still needs to have a configuration number, even though it's fixed, so it can't move at all. So the very first joint is prismatic. Because it's a virtual joint, we just say it's 0. The next one is fixed. That's the joint mass, so that one also gets. Actually, I think it starts a joint mass. So how does this work? Sorry, no. So this is base. So actually, there is a real value for the base, which is 0. This is 0 for the mast. This is a real value for the lift. This is 0 for what comes after the lift, which is arm link L4, which is fixed. So that one gets 0. So I think there just has to be one 0 before this starts. And that's probably because there has to be a fixed link at the very beginning, which is named the base link. So that is, hopefully that makes sense. If you have a question on that, feel free to speak up. Okay, so moving forward, this is a target point. It's a target point with respect to where the robot's base link is right now. So x is negative 0.04 meters, so about 4 centimeters. And so x meaning the base translation, right? So that is 4 centimeters backwards in the base translation. This next value is the y component. This is 44 centimeters. If we look at, like the frame on the robot, and actually this might be helpful to kind of go back to this 3D image here. Base link right here, that shows you the coordinate frame on the base. It's the red axis is the x-axis, right? So when we said -4 centimeters, we meant backwards along the x-axis, along that red axis for 4 centimeters. And then when we talk about, a right-hand coordinate frame, your y-axis is the green, and my thumb here, that's the blue, which is the z-axis. So when we say -44 centimeters along that green, we're talking about basically this arm extending out. And so what I want is for this arm to extend out, right? And that's why there's a 3D point around here, -4 centimeters along this green, and the last component along z is 65 centimeters up in the air, right? So that is definitely achievable for the robot. It's kind of where the robot started, where it was homed and it was kind of out with its arm, right? So the methods to do this are actually trivially easy at this point. We've got the current configuration. We've got the chain. We call inverse kinematics on it. We give it a target point, and we give it an initial position. The only reason I gave it the initial position here being the current configuration of the robot is just it was easy to give it there. You could give this anything that the solver could solve for. So if you give it an invalid configuration, the solver won't be able to solve for it, and it won't actually give you a result. But this right here, the solution, ends up being a 1D array where every single value is the actual joint configuration, right? Joint position that I should achieve in order to get to that target point. So one thing that we want to do is, okay, great, you gave me a solution, but you're iterative, you might not have converged. How do I know that this solution is good or bad? We can take that chain, forward kinematics it with that same solution, take out just the 3D point, subtract away the target 3D point, and take the norm, right, of that vector. Give me an error on how good that solution actually achieves that target point. And, it might be kind of hard to, without having seen a bunch of these, to interpret what's a good value for the error. I'll tell you that anything below e to the -3 is a pretty good value. It means that it'll be within a few millimeters of the solution. E to the 10 means that it's right on the solution. If you see something like 0.1, that means that it definitely did not converge. So it's kind of one thing to have that number. One other way to visualize this is through a 3D plot. The plot itself is a little bit hard to interpret. I mean, the first time I looked at this, I kind of had no idea what was going on. So I annotated this version of the plot to try to explain what's happening. This green, teal, and a yellow coordinate frame is your fixed base link. So green is your x-axis, teal is your y-axis, and yellow is your z-axis. You've got a base translation here. That's what this bit looks like. You've got this is like a fixed offset between that base link, which is kind of right under the RP LiDAR on the robot, to that mast, which is right under the mast that goes up and down. And so what you've got is a joint that's the lift, which can go up and down here. You've got that first offset here, which is L4, like we said, that was fixed. And then you've got variable offsets variable joint values for the L0 to L3, which actually can telescope out. Once again, another fixed offset here from the last link to where the wrist yaw starts, and then a value for wrist yaw, a rotational value. And the target point that we gave it is the red, right? So ideally, you would want to see the end of this chain kind of land on that red point. It is definitely not a very good visualization, though, so I fully understand if that's confusing. I'll try to pan around in 3D now to show what this solution looks like. So this solution has the robot, achieving the 3D point still. And it has the base moving forward. It looks like about 15 centimeters. It has the lift moving up. It looks like about to 0.8 meters. It has the arm extending out, and then it has the wrist yaw kind of pulling back in order to achieve it. So this is, in my opinion, a kind of a convoluted solution. Basically what it's done here, the IK solver, is instead of just extending out the arm, it wants to move forward and kind of move the arm right back to splay back towards that target point. So how do you solve for that? How do you kind of get nicer solutions out of this? That is done by giving it a orientation, right? So actually in the previous section, we only gave it a 3D point to achieve. It had no orientation constraint on how the gripper should be oriented at that target point. What we'll do now is we'll not only give a target point, but we'll also give a target orientation, which is 0, 0, and negative pi over 2. So what does that look like, negative pi over 2? So let's talk about this in terms of the base length frame again. So rotation over the x-axis is 0, rotation over the y-axis is 0, and along the z-axis, unit circle starts going to the right, in right-hand rule. So negative pi over 2 means point out towards the y-axis, right? Towards the negative component of the y-axis. So one other thing that I've done here, I've given it a pre-target orientation. This is so that it has basically, I know that it can solve to an orientation for that target point if I give it a pre-target orientation very easily. But I know that if I give it just the target orientation by itself, it might not converge. So I basically help it along the way. I do a coarse initial step, and then I have it solve the rest of the way. And I'll show you how we're going to do that in the demo later too. It's a pretty neat trick. If you have the robot kind of like where it needs to be already, and then you give another target point that's near to where that was, it's not too difficult for the robot to do the IK to solve from that point on. And you can also always mess with the actual parameters inside this method in Inverse Kinematics. And there's a link to the API docs for that, actually right there. Cool. So you get the current configuration, Q init. You do inverse kinematics for the target point with the pre-target orientation given that Q init. You get the configuration in the mid. Maybe that did not fully get you the solution you wanted. So now you give it to the same method again with the same target point, but then now the target orientation with now the middle solve. And it gets you the rest of the way there. Solving for that, printing it out, we have that 1D vector again for the configuration of the robot. And calculating the error for it again, we find that it's even better than it was before, negative 13. So I'm going to plot that out. And this to me is kind of what I was looking for in the previous solution. I wanted the arm with the yaw out to reach that point. And so I will now ask it to run that solution, right? We've solved for it. So we're going to create a method called move to configuration. It's going to take in the tool once again so that you can support with both of the grippers. And then it's going to take in that configuration. The robot's already stowed, but just to be, starting in the configuration we gave it, I'm going to stow it, and then I'm going to give it that solution, Q solution from up here. So okay. Hopefully you can see it on this camera stream here, but this point is actually the point that I gave it as a target point up here. And now what it's done is moved, it's just its arm to reach that point. What whereas previously it would have moved the entire base and the arm kind of would have splayed back to reach this point. Cool. Okay, so this is working. Why don't we tie it all together? So this is a method called move to grasp point. It takes in a target pose as a 4x4 matrix that composes all of the rotations and the x, y, and z into a matrix. And then we give it a pre-target pose if we want. By default, that's none. And if we don't give it, then it won't solve for it. And then we also have another argument here called plot prompt. So it will plot it and it will prompt you if you want to actually execute it. So this way you can stop, not run it if its solution looks kind of bad. So this guy, the target point is somewhere back here, and it looks like it hasn't fully solved for that point, so we're not going to execute that. Cool. And then this is another method called get current grasp pose. So this is doing the forward kinematics. And you can kind of, from this point, take this method, move to grasp goal, and be able to achieve any target point that you give it using the 4x4 matrix that this achieves. Right. So one paradigm here is, okay, I want the gripper to achieve this 3D point on the whiteboard. Let me manually move the robot using like the run stop here. Call this method, it gives me that matrix, and I feed that matrix back into the solver later on, move to grasp goal, and it will automatically do it. If this was false, by the way, it would just go ahead and execute it. So you could also have these queued up a few at a time, and it would automatically achieve each of the points that you wanted. Another way, by the way, to create these 4x4 matrices, so these are called homogeneous transformations. There's a lot of methods that you can use as part of the IKPy library or even just NumPy to compose 3 angles, rotational angles, like Euler angles, right? Roll, pitch, yaw, plus a 3D component into one of these matrices. So I won't go into that here. I thought I'd have more time. This ended up taking a little bit longer than I suspected that it would. So we won't tackle in the next 9 minutes an actual demo of writing Hello World on the whiteboard. But I hope it's kind of clear how you might do that, right? If you are able to encode each letter's points in 3D space plus orientation, which orientation is always pointing into the whiteboard. And then your points for an H, for example, right? You start at the top left, you pull down to the next point, right? And you just queue those up as part of move to grasp goal. The robot can pull down the marker and it can write that first stroke of the H. Then it can move back to the middle, right? And you can continue to queue those up until you've got the full letter H. One thing that I was hoping to do in this demo was actually import the Hello Robot SVG, the logo, take out the path from that, and then interpolate along that to get a bunch of points. And the nice thing about that is, if you've got a bunch of points along a path that you're solving for, once the IK solver has the Q init for the previous solve, it's super easy. You can imagine the next point on that path is maybe a centimeter away. It's super easy for the solver to return a solution within a few milliseconds to get to the next point.